Hello viewers, welcome to this next lecture on the NPTEL MOOC course on mathematical portfolio theory. You would recall that in the last class we started talking about the optimal portfolio in the case of a continuous time setup, and we looked at the wealth equation wherein we consider a portfolio comprising of a stock with the stock following the geometric Brownian motion and a bond. And based on that wealth equation, we talked about how we can optimize the expected utility of the final wealth level, and this resulted in us getting the equivalent of the dynamic programming in case of the continuous time setup, namely the Hamilton-Jacobi-Bellman equation. So, in today's class we will continue our discussion on the HJB equation, and we begin with a couple of examples, and then what we will do is that we will move on to the inclusion of the case where we also, in addition to the wealth process, must also consider what is the consumption process, and then we will look at a description of that. So, accordingly we begin this lecture with this example. So, here let us consider that the utility function is log x, that means natural log of x, and we assume that the solution to the HJB equation is of the form V T x. Remember, the HJB equation involved the value function V T x is equal to log of x plus some constant k into capital T minus small t. So, that is for some constant. So, actually the constant is k, and here of course, we need the condition that V of T x is equal to log x, which obviously is satisfied, because if you put small t is equal to capital T, this term becomes 0 and you are only left with log of x. So, with the assumption of this form for the value function, therefore, we obtain that V of t, that is partial derivative of V with respect to t, this is going to be minus k, V of x is going to be 1 over x, and V x x is going to be minus 1 over x square. So, now recall that what was the HJB equation? The HJB equation was V t minus theta square over 2 V x square over V x x plus R x V x is going to be equal to 0, subject to the condition that V T x is equal to log of x. So, now what we do is that we can substitute these three evaluated expression in the HJB equation. So, substituting V t, V x and V x x in the HJB PDE, we get minus k minus theta square by 2 1 over x square divided by minus 1 over x square plus R x into 1 over x is equal to 0, which implies that my k is going to be equal to r plus theta square over 2. So, therefore, the optimal portfolio is given by pi of t, and we indicate the optimal portfolio with a hat, and this is, you recollect, was theta over sigma into x of pi hat of t, or equivalently the optimal portfolio of wealth to be invested in the stock is a constant given by pi hat of t. So, this is a capital pi hat. So, this is little pi hat of t that we have here divided by the wealth process under this little pi hat of t, and this just turns out to be nothing but mu minus r over sigma square. Okay, let us now consider another example. So, let the utility function u x be 1 minus e raised to minus alpha x, and let us assume, based on the form of the utility function, the solution to the HJB PDE is of the form V t x is equal to 1 minus f of t instead e raised to minus g t into x. So, again we recall the HJB equation. What was this? This was V t minus theta square over 2 V x square over V x x plus R x V x equal to 0, with V t x being equal to 1 minus e raised to minus alpha x. Okay, so, we can now evaluate these values. So, after evaluating V t, V x and V x x, we get accordingly we will get e raised to minus g t of x within bracket minus f prime of t. So, this f prime of t will come from the derivative with respect to t. So, it is minus f prime of t plus f of t g prime of t into x, plus we have half theta square f of t plus r g of t f of t is into x. This is going to be equal to 0. And now, what you are going to do? So, obviously, this term is not going to be equal to 0. So, accordingly, I have this entire expression being equal to 0. So, what you can do now is we will now look at the term which comprises of f prime. So, I have an f prime here and f here. So, what we are going to do is that we are going to segregate these terms in which only involve f or f prime, that is the function f, and then those which involve both f and g or f or g prime. So, these two are going to be collected together. So, one way of achieving that this is going to be equal to 0 is that this plus this are going to be 0 and this expression plus this expression is going to be 0. So, accordingly, we get f prime of t minus half theta square f of t is going to be equal to 0, and for this along with this expression we will get a common factor of f t, which obviously cannot be 0, because in that case v of t x is just going to be a constant. So, accordingly, we will have that our g prime of t from here plus r g of t is going to be equal to 0 from this term. Now, you observe that both of them these are first order ODEs or ordinary differential equation. So, now what we do is we need in order to solve this first order ODEs we need some condition. So, that can be obtained from the fact that v of t x is equal to 1 minus e raised to minus alpha x, and we had assumed our v little t of x is 1 minus f of t into e raised to minus g t of x. So, this is going to give us v capital T x is going to be 1 minus f of capital T e raised to minus g of capital T into x. So, what we do is that we equate both this expression, and accordingly what we get from both this expression is that we have the boundary condition or the final condition are, from here you get, so the ones will cancel out. So, this f of t is going to be equal to 1 and g of capital T is going to be equal to alpha. So, then we can solve this first order ODE subject to this condition for f of t. So, the solution is f of t is equal to e raised to theta square into t minus t over 2, and then we can solve this equation for g with respect to this condition, which gives us g of little t is alpha e raised to r of t minus t. So, this is obviously going to end up giving us what is v of t x. So, then using that we can obtain the optimal portfolio is pi hat of t x. Remember that this was minus theta over sigma v x of t x over v x x of t x, and if you replace the value. So, you have found out the solution of v from here. So, remember v is equal to 1 minus f of t into e raised to minus g t of x. So, you can calculate v x and v x x from here. You end up eventually with the form theta over alpha sigma into e raised to minus r t minus capital T. So, we now consider the case of the investor who derives utility from consumption also. So, this means that in addition to the wealth process, now the consumption process also has to be taken into consideration. So, recall that for a continuous time setup, the consumption C is a non-negative adapted process. So, accordingly, let the total cumulative consumption be denoted by C of t, which is integral of 0 to t C of u du. So, now we are in a position to state the problem. So, the mixed, that means it is a combination of terminal wealth, consumption, utility, maximization problem is given by. So, we will look at what is going to be the utility of the final wealth, that is x of t, and the utility of consumption and the integral of that from 0 to t of du, and this utility of the wealth, this is going to depend on pi and c, and since this is a random variable. So, obviously, we need to calculate its conditional expectation E subscript t comma x, and you take the supremum of this over the portfolio process pi and the consumption process c, and this results in the value function which depends on time t and the wealth level at time t being equal to little x. So, supremum over pi c, conditional expectation of u1 as well as integral of u2. Now, this is subject to the wealth equation dx pi c is going to be Rx pi c plus pi into mu minus r dt plus pi sigma dw. So, this is the expression for the wealth process without the consumption, and along with it now we include a term for the consumption. So, you observe that this was the change in the wealth level without the consumption was given by this factor, and then the change of the wealth level is also going to be affected by the consumption C over the interval of dt, which has to be subtracted. So, accordingly you can show that for the case where you consider both wealth and consumption, the HJB PDE is Vt plus supremum over pi c of half pi square sigma square Vxx plus pi into mu minus r as before, but we have a new term minus c Vx plus u2 of c, that is the utility function for the consumption, plus Rx Vx is equal to 0, subject to the condition that Vtx obviously is going to be u1 of x. Okay, so now we need to take the supremum of this expression here. So, so let me identify this expression as star. So, taking derivative of the expression star with respect to C, we get the following. So, there are only two terms comprising of C, this term and this term. So, we accordingly we take the derivative in order to obtain the optimal consumption as C hat being equal to u2 prime inverse of Vx t x of t driven by the optimal portfolio pi hat and the optimal consumption C hat. So, here the notation, this inverse notation is nothing but the notation f inverse of f x is going to be equal to x. So, now it is time to consider an example to accommodate this consumption. So, again we use the utility function to be the log utility, and the question that we want to address is what is going to be the optimal portfolio and of course, what is the optimal consumption. So, here let V t x, the value function, be f of t plus g of t into log x. So, maximizing the term u2 of c minus c v x gives that c hat of t x is equal to I2 of Vx Tx, where I2 is the inverse function of u2 prime. Now, the HJB PDE with this assumption for Vtx, this reduces to f prime of t plus g prime of t log x plus theta square over 2 into g of t plus r g t minus log of g t plus log of x is going to be equal to 1. So, the equation for g t will then be what? It is going to be log of x. So, actually it is the equation I should say for log of x, that means this term and this term. So, this is going to be log of x into g prime of t plus 1 is equal to 0 with g of t equal to 1. So, hence the solution is g of t is going to be capital T minus small t plus 1. So, once you have got the value of g of t, you can replace it in this expression and then you can one can solve for f of t, but that is not needed. I mean, of course, you have to do this if you are trying to calculate V, but we are trying to calculate what is the optimal portfolio and consumption. So, evaluation of f t is not required. So, therefore, the optimal portfolio is pi hat is equal to minus theta over sigma V x over V x x, and this is theta over sigma into x, and the optimal consumption is c hat of T x, and remember that c hat of T x is going to be given by the inverse of u 2 prime. So, u 2 prime was 1 over x. So, the inverse of that is this is going to be 1 over V x into T x, and this turns out to be equal to x over capital T minus small t plus 1. So, thus you have obtained the optimal portfolio as well as consumption in case of the log utility. So, we now come to what is known as the duality or Martingale approach to utility maximization. So, we begin this part of the class with the discussion of the Martingale approach to the single period binomial model framework. So, as before, let S0, so we are considering a single period model. So, accordingly we say that let S0 and S1 denote the price of the stock at the beginning and end of the period 0 1. So, according to the binomial model, let S1 have two values. So, we know that in the binomial model S1 will have two values. So, let those values be S of u with probability P or S of d with probability 1 minus P. Further, let R denote the single period return. So, just to note that SD is less than SU, and this must lie between this must sandwich 1 plus R into S0. So this means that if you invest an amount of S0 in a risk free asset, it will go up to the value of S0 into 1 plus R at time 1, and this must lie between the lower value of the stock SD at time 1 and the higher value of the stock SU at time 1. Now recall that the wealth equation starting with the wealth level x0 equal to x is given by, so this wealth equation at t equal to 1, this is given by x of 1. And how do we get this? So you start off with an amount of x and you buy delta naught stocks whose total cost is delta into S0, and you invest this in a risk free asset. And this delta stock at time 1, it gets the value S of 1 into delta. So that is the value of the delta number of stocks at time 1, and this is equal to x of 1. Now this is like the terminal wealth. So what we need to look at is that, since x of 1 is the wealth at the terminal point t equal to 1, so accordingly the expected utility of the terminal wealth is, what is this? It is going to be the expected utility of the terminal wealth, that is x of 1. This is going to be the utility of, so x of 1 can take two values, namely xu and xd. So the corresponding utilities are going to be u of xu and u of xd, and the respective probabilities are p and 1 minus p. So the expected utility is going to be sum of these two. And what is the goal? So the goal is to maximize the expected utility. Now let us be more specific about what my xu and xd are going to be. So what is going to be xu? Xu is the wealth resulting from the stock going up to SU. So xu is going to be delta into SU from this term, plus of course x minus delta S0 into 1 plus R, and in an analogous manner xd is going to be delta SD plus x minus delta S0 into 1 plus R. So therefore, what is going to be the expected utility here? So this is going to be, so the expected utility of the terminal wealth now, in more precise term, this is going to p into xu. So I will replace this form of xu. So it is the utility of delta SU plus x minus delta S0 into 1 plus R plus 1 minus p into utility of this, which is delta SD plus x minus delta S0 into 1 plus R. And my goal is essentially to maximize this utility. So accordingly, taking the derivative of, let me call this double star, with respect to delta and setting equal to 0, we obtain that p of u prime of xu into the derivative of xu. So this is going to be Su minus S0 into 1 plus R plus 1 minus p u prime of xd into derivative of the argument, which is Sd minus S naught into 1 plus R, and I set this to be equal to 0. So this expression, rather this equation, can be rewritten as the expected utility of u prime of x of 1 into S1 minus S0 into 1 plus r equal to 0. So, you see the random variable here is u prime of xu into this expression and u prime of xd into this expression. So, x1 u prime of x1 will be u prime of xu with probability p and u prime of xd with probability 1 minus p, and S1 minus S0 into 1 plus r is going to be this expression with probability p and this expression of with probability 1 minus p. So, if I consider this entire thing as a random variable, these two random variables, so with respective probabilities p and 1 minus p, so this can be written in the compact form as the expected value of u prime of x1 into S1 minus S0 into 1 plus r, and this is going to be equal to 0. And then which gives that, so I can solve this for S0, and this is going to be expected utility of u prime of x hat of 1, and I am using here x hat because this is an optimized value, over expected utility expected value of u prime of x hat of 1 into S1 over 1 plus r. So, here the notation that we have used here x hat of 1. So, this notation x hat of 1 is the optimal terminal wealth for the investor. So, we now introduce the notation, and we will call this expression here. Let us call this, since this depends on time 1, let us call this some z of 1, and this is defined as u prime of x hat of 1 over expected value of u prime of x hat of 1. So, this implies that if we take the expectation, the numerator and denominator will become identical. So, the expected value of z1, this is going to be equal to 1. So, using this notation that is z1, we get, so this will result in this value of S0 being written as the expected value of z1 over 1 plus r into S1. Now, see, z of 1 is u prime of x hat of 1. So, obviously, this is a random variable. So, this random variable z1 is referred to as the change of measure, and it will soon be clear why we are calling this as change of measure. Also, this factor z1 over 1 plus r is called the stochastic discount factor. Now, I want to make an important observation. So, if you look at option pricing, you will see how important this observation is, and that there is another interpretation of the formula, that is use of a new probability or change of probability measure. So, accordingly, we will define P star to be is equal to P into u prime of x hat of u divided by the expected value of u prime of x hat of 1, and we define accordingly 1 minus P star. This is going to be 1 minus P into u prime of x hat of d over expected value of u prime of x hat of 1. Now, here p star and 1 minus p star may be viewed as the new probabilities, or what is known as risk neutral probabilities. Of SU and SD. So, remember that earlier we had the probability p and 1 minus p, and this will now be changed to p star and 1 minus p star. So, this and that is the reason why. So, since this is a change of the probability measure, so that is the reason why we had referred to Z1 as the as change of measure. So, accordingly, we can write that then S0 is equal to E of Z1 over 1 plus R S1. This is one expression for S0 we had got, and this can then be, so this is one expression, and then we reconcile it with the previous expression, and it can be shown that this is nothing but E star of S1 over 1 plus R. And here we note that the notation E star denotes the expectation using the risk neutral probabilities. So, this expectation here makes use of the probability p and 1 minus p, and this expectation here uses the probability p star and 1 minus p star. So, the reason why these are called risk neutral probabilities is that you observe that here we have S0 is equal to E star S1 over 1 plus R, and this will give us that the expected value of S1 is going to be S0 into 1 plus R. So, if we had invested an amount of S0 directly in a risk free asset, this would grow to S0 into 1 plus R, and this is going to be the same as the expected value of the stock price at 1, which is a random variable. And since the expected stock price at time t equal to 1 under p star and 1 minus p star becomes the same as that you obtain from a risk free asset. So, the probability which causes this to be equal, namely p star and 1 minus p star, accordingly is called as the risk neutral probability. So, in general, for a multi-period model, with R being the constant risk free rate for each period, we obtain that S of t divided by 1 plus R raised to t is E t star of S of t, that is S of capital T divided by 1 plus R raised to capital T, where I have introduced this subscript t. So, here this notation E star with subscript t is the conditional expectation conditioned on information available at time little t. Now, if we introduce the notation m of t as S of t divided by 1 plus R raised to t, then m t, so from here we get m t is equal to E t star of m of capital T. And a process MT is a martingale if MT is equal to ET star of m of T. So, a martingale process is defined to be a process MT which satisfies this property, and in particular if I choose my MT to be this expression, then the above expression here reduces to this definition of martingale, and hence the discounted stock price process is a martingale. Now, we observe that Z1 can take two values. So, remember that this depends on whether the stock goes up or down. So, accordingly, depending on SU and SD, it can take two values ZU and ZD with probability P and 1 minus P respectively. Now, since expected value of Z1 is equal to 1, therefore, so by definition of Z1 this expectation is 1. So, therefore, P into ZU, remember ZU takes the value with probability P, plus ZD which takes the probability 1 minus P. So, it is 1 minus P into ZD. So, this is the expected value of Z1 and this is going to be equal to 1. Also, if you observe carefully, 1 plus R as 0 is going to be, so for this purpose I am going to make use of the fact that S0 is expected value of Z1 over 1 plus R into S1. So, S1 can take two values. So, this becomes 1 plus R S0. So, this is going to be ZU into SU, and the other value would be, so these are going to be the values of Z1 S1. So, these are going to be ZU SU or ZD SD with respective probabilities P and 1 minus P. Okay. So, then what we get is we now solving for ZU and ZD, we obtain that ZU is equal to 1 over P into 1 plus R S0 minus SD over SU minus SD, and ZD is equal to 1 over 1 minus P into SU minus 1 plus R S0 into SU minus SD. So, this brings us to the end of this lecture. Just to do a recap of what we have done so far. So, we picked up from our formulation for the Hamilton-Jacobi-Bellman equation, and then we looked at two examples to determine what is going to be our optimal portfolios. And then we moved on to the situation where we include, in addition to the wealth process, we take into account what is the consumption process, and then we stated the Hamilton-Jacobi-Bellman equation when both these processes are involved, and we looked at one example. And then we moved on to the case of the Martingale approach for portfolio optimization, and in today's class we set up what is going to be the background for that, and we also identified a very important concept that is used in finance in general, that is the notion of risk neutral probabilities. So, in the next class we will continue our discussion and we will look at how we can now make use of this Martingale approach in order to determine what is going to be an optimal portfolio. Thank you for watching.